In this problem or video, we're going to work an elastic collision problem. A 3 kilogram object is moving at 10 meters per second. I call that V1, 10 meters per second. And we have, this will be M1. So M1 is equal to 0.3 kilograms. And it strikes into mass 2, M2. And M2 is moving with the speed V2 initial of 4 meters per second. And then after that, I'm going to have the two blocks again. And let me change colors of the pen. So the blue block here is going to be going at some new velocity, V1F. And the red block is going to be going at some new velocity, V2F. And one thing that I do know, V1I, that was 10 meters per second, is going to be less than that. So V1F, I should say, is got to be less than V1I. So what I know is that V1F will be less than 10 meters per second, because when it hits this red block, it will apply a force, and that force will decelerate this red block. Now, let's see what else we know about this thing. It says, what is the change in the kinetic energy of the 1.5 kilogram object as a result of this collision? All right, so now this is a couple of ways to work this problem. This problem is conservative, so you can work it to where you find V2F and subtract the kinetic energy it initially had, or equally you can solve for the kinetic energy that the blue block had and the kinetic energy it has at the end, and subtract that, because the energy that's lost by the blue block will be the energy that's gained by the red block. How do I know that? I know that because it says that total kinetic energy is conserved. It's an elastic collision. So to do a collision, first thing we need to use is momentum. So we're going to use momentum. I have initially M1 V1 initial plus M2 V2 initial has to equal M1 V1 final plus M2 V2 final. Now, in our case, if we'll just realize that I'm going to divide all of these by M1. Don't have to be M1, but that's the one I'm going to choose to do. If I do that, I got V1 final plus M2 over M1 V2I plus, equals V1F plus M2 over M1 V2F. And the nice thing about doing that in this particular problem is that M2 divided by M1 happens to be a nice integer. Happens to be 1.5 kilograms divided by 0.3 kilograms happens to be 5. So we have V1I is, plus 5 V2I is equal to be V1F plus 5 V2F. And like I said, now my choice is I can either solve for V2F and get that, or I can solve for, back over here, for V1F. And it really doesn't matter. I need to eliminate one of the variables, either the final velocity of block 2 or the initial. It does ask for the kinetic energy change of the second block, so I guess since it asked for the second block, we should work with the second block. So I'm going to get rid of, or would like to get rid of, V1F. So if I do that, V1F is going to be equal to V1I plus 5 times V2I minus V2F. And that's equation 1. Now, I have too many unknowns in that equation to solve it. I can't solve for V2F, and I can't solve for V1F because I have one equation and I don't know the speed of block 2, the red block, nor do I know the final speed of the blue block. But it says it's an elastic collision, so we know also that energy is conserved, which will give me another equation. So for energy analysis, I have 1/2 m1v1I squared plus the kinetic energy of the second block, 1/2 m2v2I squared, and all that has to equal 1/2 m1v1 final squared plus 1/2 m2v2 final squared. And likewise, we can do some things to simplify this equation. The 1/2 can be canceled, so I'll just go ahead and whack out the 1/2 across the board. It's also possible to divide both equations by m1, so I'll do that. v1I squared plus m2 over m1 v2I squared is equal to v1F squared plus m2 over m1 v2F squared. And I can go ahead and replace that with 5. v1I squared plus 5 v2I squared is v1F squared plus 5 v2F squared. And in the same way that I did previously, I want to simplify this equation just like I did over here. So if I do that, v1F squared is going to be equal to v1I squared plus 5 times v2I squared plus v2F squared. I'm sorry, that's a minus. And that's equation 2. And now I want to combine equation 2 with equation 1. So if I square this equation, I can put it into here. So square 1 and combine with 2. And so really most of the problem, except for knowing and writing the original conservation of momentum and energy equations for these problems, is a demonstration of your expertise in algebra. I've got v1I plus 5 times v2I minus v2F. All of that has to be squared, and that has to equal v1I squared plus 5 times v2I squared minus v2F squared. Okay, now let's see. I have v1I squared plus this times that times 2, 10 v2I minus v2F v1I plus the square of the second term, 25 times v2I minus v2F squared is equal to v1I squared plus 5 times v2I squared minus v2F squared. Running out of page. Wonderful. Just nothing like a whole pile of algebra to have to do something with. Unfortunately, it's not like there's a way to simplify this a lot. Well, this is a number, and I certainly can replace it by the number. this number is 10 squared, which is 100. And I can do that. Some of this I can't do anything about. So this is 100. I'll leave off the units. That's 100 meters squared per second squared. This is 10. This is 10 meters per second. So this is 100 meters per second. And then it's multiplied by 4 meters per second minus V2F. This over here, this is 25 times 4 meters per second minus V2F squared. And all of this is equal to 100 meters per squared second squared plus 5 times 4 minus V2F squared. I'm sorry, this is not 4, this is 16. Now I can kill this and that, but you can see that this is like an x. There's a bunch of them. There's an x to the first power. There's an x that's going to go to the second power. And there's another x over here, the second power. So we're going to need the quadratic formula to solve this problem. And I'll pick that up in the next video.